What's up guys, and welcome to this video. This is part 3 of our this video series, and in the previous part we went over elastic and inelastic collisions, and in this video we are going over impulse. Okay, so basically impulse helps to try and join together momentum and forces and time and all the stuff we've learned so far, okay, into one kind of equation, because the amount impulse basically describes how much of a force will be transmitted over, or how much of the momentum will be transmitted over the period of some time. Okay, so basically the definition, so let's start off with that. So impulse is the product of the net force and the contact time. Okay, so we can say that impulse, okay, so impulse in the form of an equation is equal to, let's switch colors. Okay, impulse is equal to the net force, F net, times delta T. Okay, and the net force has got units of newtons, and time has got units of seconds, so that is in Newton seconds. Okay, and an impulse causes a change in momentum. So, but an impulse causes a change in momentum. Okay, so therefore we can say that impulse is equal to change in momentum, which we've already discussed. Okay, now we can go and equate these two equations, and we can say that F net from equation 1, delta T, is equal to delta P. And delta P, we've already said, is equal to our mass times our velocity final minus our velocity initial, or equals to m delta v. Okay, and obviously the units, because these are all impulses, it's equal to Newton seconds. Okay, and an equivalent unit for Newton seconds is from momentum. We know this momentum has got units of kilograms meters per second. So these two units are equal. Let's just write this like this. It might be easier. Okay, so therefore, in terms of momentum, we can now define Newton seconds. So Newton second law, F net equals ma, can be defined in terms of momentum. Okay, and the definition goes, the net force acting on an object is equal to the rate of change of momentum. Okay, so F net, in the form of an equation, we can say that F net equals delta P over delta T. Okay, and that is in units of newtons. Okay, remember, let's just make sure our original definition of F net from Newton's second law is F net equals mass times acceleration. Okay, so mass has got units of kilograms and acceleration has got units of meters per second squared. If we look at our new definition, if we look at F net is equal to delta P over delta T, this has got units of kilograms meters per second divided by change in time, which is in seconds. So the equivalent unit of this is kilograms meters per second squared. And clearly, these two units are equal. Okay, so just remember that we can use units to just verify what we're doing is correct. Okay, so let us actually jump into an example. Okay, so this is quite an abstract example. Okay, so in this section, some of the more important equations are this equation here, this equation right here, and this impulse equation. I mean, they're both the same, but that one right there. Yeah, so we've got three kind of key equations. Okay, but let's assume, for example, let's say we're given the force time graph, and we want to determine the impulse. Okay, so the force time graph, let's say, looks something like this. Okay, let's say it goes from 0, 10, 20, 30, 40, 50. Okay, and that's going to be time, obviously, and this is going to be newtons. Okay, and let's say that it goes up in 10, 20, 30, 40, 50 to 50. Okay, and at 25 we reach 50, and it looks like a nice triangle. Okay, and we want to determine the impulse, right? Using this equation right here, F net equals delta P over delta T, we can say, and this is impulse, okay, so delta P equals F net delta T, and that's just equal to the area under the force time graph, right? Because if we say force, which is in newtons, so this would be force times time is F net delta T. So the impulse is equal to a half times my base, which is 50, times my height, which is 50 as well. So therefore the impulse, or not the impulse, but we can say, the impulse is equal to, let's plug this into our calculator, that's 25 times 50, which is equal to 1,250. And it's got units of kilograms meters per second. Okay, so that's how we work out the impulse using our force time diagram. Okay, so now let's go into something that's a bit more mathematically intensive. So let's say we have another example. Okay, a common example that we almost always come across is the concept of a bullet going through something or something along those lines. So we can say that in this example, a bullet of mass equals to 50 grams travels to the right and strikes a target at 450 meters per second and exits at 300 meters per second. Okay, the contact time is given as 0.001 seconds. Okay, so very small contact time. Okay, and we want to determine the following. Okay, first we want to determine the change in momentum. Okay, then the second thing that we want to calculate is the impulse. And the third thing we want to calculate is the net force experienced by the bullet. Okay, so let's get into that. Okay, so first of all we want to determine, so question A says determine the change in momentum. So change in momentum equals delta P equals mass, final velocity minus initial velocity. Okay, and we're going to take right as being positive. Let's actually draw out a schematic, because that's quite important as well to understand the problem correctly. Okay, so we have a bullet, okay, and it is traveling at, and let's say here's a target. Okay, so before the collision, velocity initial is equal to 450 meters per second, as given in the question. The mass of the bullet equals 50 grams, and after the collision, the velocity, so after the collision, the velocity final is equal to 200 or 300 meters per second, and they're both in the rightwards direction. Okay, so obviously then it makes sense to take right as being our positive direction. So then using this we can say our mass is 0.05 kilograms, remember mass is in kilograms, velocity final is equal to 300, and velocity initial is equal to 450. So if we plug this into our calculator, we get a value of minus 7.5 units of kilograms meters per second. Okay, and that basically means the impulses, or the momentum, change of momentum, is leftwards. Okay, so it's opposing it, which makes sense, because basically the collision with this target causes a net force in the opposite direction to the direction the bullet is moving. That slows it down, so we're expecting a negative impulse. So therefore we can say that is our final answer for that. Okay, then our impulse. Remember, we defined impulse already as the change in momentum. So impulse is actually equal to delta P, which is equal to minus 7.5 kilograms meters per second. Okay, so quite easy there. And then finally, we want the net force, C, and we know that F net equals delta P over delta T. Okay, and we've calculated delta P, and we have been given delta T, so we can say it's minus 7.5 over 0.001, which was given in the question right here. Okay, and we can just plug that into our calculator, and we get a value of minus 7,500, and it's a force, so the units are going to be newtons. Okay, and the minus sign just indicates left once again. Okay, so that's all that question really does. There's nothing too difficult about that, but I want to do a very similar question and show how things can change based on our directions. Okay, so let's go into the next example. It's very similar in that we have a bullet once again. Okay, so let's actually copy this. Let's use the same scenario. Okay, so we have a very similar scenario right here. Okay, so a bullet has mass of 50 grams, travels to the right and strikes the target at 450 meters per second. Okay, we want to determine which scenario results in the greatest and least impulse. Okay, so scenario A, we're going to say, is when the bullet exits at 250 meters per second. B is when the bullet stops in the target. Okay, and C is going to be when the bullet rebounds at 250 meters per second. Okay, so we have three scenarios. So we want to work out the impulse for each of these. Okay, so for A, our impulse, okay, so let's just think about this, right? Before we even get into it. Impulse, so we really wondering about, so when the bullet goes through at 250, it means that there was a force, but it was relatively small in that it didn't stop the bullet. Okay, so the next situation is when the bullet stopped. So we're expecting a larger force, and so a larger impulse to occur. And then when it's rebounded, we're expecting it to have the highest impulse because it's actually stopped the bullet and then given it sufficient, let's say, energy that it's actually caused the bullet to travel in the opposite direction. So that's what I would expect. But let's just prove this mathematically. So the impulse for the first one is equal to delta P is equal to mass final minus initial, and we will take the rightward direction as it being positive. Okay, so that's actually generic, so we can actually start A right here. So impulse for A equals, the mass is 0.05, the final velocity is going to be 250, the initial velocity is 450, and so if we plug that into our calculator, we get a value of minus 10 kilograms meters per second. For B, so impulse B is equal to 0.05, the final velocity is 0, the initial velocity is going to be minus 450, so once again, plugging that into our calculator, we get a value of minus 22.5 kilograms meters per second. And finally, for C, impulse C is equal to mass. It's rebounded, so that means it's changed directions, right? It was traveling in this direction. When it rebounds, it changes direction. So our velocity is going to be a negative. This is very important. Minus 250 minus 450 is equal to, and let's plug that into our calculator, and we get a value of minus 35 kilograms meters per second. No, kilograms meters per second. Okay, so as we can see, the impulse of C is greater than the impulse, actually we should do like this, impulse of A is less than the impulse of B, which is less than the impulse of C, which is what we expected. We expected to take a lot more impulse or change a lot more momentum when we're being rebounded than when we're allowed to pass, or when the bullet's allowed to actually pass through it. Okay, so those are the questions that I wanted to do in this video. Those are very analytical types of questions. So the next video, we're going to go into more of a theoretical kind of questions where we have to explain a certain phenomenon with respect to impulse, force, and delta T with respect to this equation right here. So Thanks for watching, guys. I hope you guys found this video quite useful. Once again, when we're looking at an FT diagram, the impulse is equal to the area under. Okay, so thanks for watching, guys. I hope you found this useful.